Okay, now we are ready to start. Zoltan, you are ready?
Yeah.
Okay.
Thank you very much.
So it's our regular seminar, which is by Friday, on Fridays, at this time usually. And now we are happy to have here a lot of Hungarian people, including our speaker today. Yes, Zoltan Furedi, who will speak about hypergraphs, but I don't remember the exact name of the topic.
Thank you. Thank you very much. Thanks. Thanks for coming. Thanks so late, and I will talk about list counting problems. Now, but before we define these things, I introduce some hypergraph results, what I hope most of you are familiar with. It's the first tools from hypergraph theory. Hypergraphs. Now, one of the first excimer problems was proposed by Bernstein, and it was investigated by Paul Erdos in the 1960s. Actually, he wrote 3 papers on it about this function. What is M of R? What is M of R? The minimum size of a hypergraph where H is R uniform. Meaning these are R subsets. So the hypergraph is just a family of sets E1, E2, EM, each of them of size R. And no matter how we cut into 2 parts, there will be a monochromatic part. So in other way, the chromatic number and the chromatic number of H exceeds 2. So in another way, if the union of EI is S, so we have a S element underlying set, and we have the R subsets. And no matter how we cut into 2 parts, there exists an edge contained in S1 or an edge contained in S2. So that was what we mean 2-chromatic, 3-chromatic. M2 is just pairs. The smallest graph of chromatic number 3. So that's a triangle. Actually, that's the only example, kind of. Now, it's not difficult to prove that M of 3 is 7. And I show this example because this is my favorite hypergraph. That's the the example, the hypergraph has 7 edges, 7 triples. And actually it will have 7 elements too. So the hypergraph in question is what we call it projective geometry of order 2 and dimension 2. The sets are, so the underlying set, there are many ways to write it down, but the nice way is to write it as a finite field minus a 0 vector, and the triples, so the finite field has 2 elements, the 3-dimensional space has 8 elements. Take out the 0 vector, I got 7 vectors. Each vector has some zeros and ones, the only coordinates, and we put so x and y and x plus y form a triple. So we can make another drawing of the same hypergraph. That's more well known maybe. The lines indicate the triples, also this circle, and the 7 elements are labeled like 0, 0, 1, 1, 0, 0, 0, 1, 0. And here comes the sum, which is 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So, and the 7th triple consists of these 3 elements. Okay? So, and otherwise it's the Fano plane. And it's easy to see that no matter how we cut the Fano plane into 2 parts, a full line, 1 triple, we will miss. We cannot cut simultaneously. Now, there is a much simpler example, and this was observed by Paul Erdos, that M of R exists, and it's always at most 2R minus 1 choose R, because we can take S as a 2R minus 1 element set, and our hypergraph is all R subsets. Now, again, it's clear that actually this hypergraph is this one, then R is 1, oh, R is 2. So it's clear that if we take this complete hypergraph, complete R graph, then no matter how we cut, in the larger part we will have an edge. Now, it took some time, and this problem has a long history, and it was it's very easy to prove that the true order of the magnitude, that's already a theorem, of M of R is exponential. This is, of course, because 2R minus 1 choose R is at most like the sum of dinomial coefficients, so it's at most 2 to the R, 2R minus 1. So it's exponential, and one can make an exponential lower bound easily. Well, the upper bound, usually a construction. Okay, so we need a construction. And the lower bound, we need an algorithm to color. Now, this algorithm, in this case, and actually in every proof, well, almost every proof, what we will show, what we will see later, is probabilistic. So we will make a probabilistic algorithm. So we have to show that if a hypergraph is small, then we can cut every edge simultaneously. The classical proof of this one is nothing else than well, the input is the hypergraph. Is a hypergraph which is R uniform, a family of R sets, and not too many hyperedges, less than 2 to the R minus 1. And we are looking for a cut. We're looking for a cut. So we take the underlying set S and we make the cut in the following way, that every element is colored red or blue by probability 1/2. With probability, so every element, so element X in S, we take an element, and the probability that X belongs to R is exactly 1/2. And also that it belongs to blue, that's another 1/2. Okay? And we do it independently and simultaneously. So with all the elements, every vertex of the hypergraph is labeled red or blue, and then what is the probability that a given edge is monochromatic? And this probability can be calculated very easily, because we have the edge EI, it has R elements, and every element goes to red with probability 1/2. So it is 1, because it's independent, the probability is 1 over 2 to the R, that it's red, and another 1 over 2 to the R that is blue. All elements blue. So that's the probability of a single edge is monochromatic. So the expected number so the probability space again is all colorings. Every vertex is colored with probability 1/2, red or blue, and then the number of monochromatic edges is, well, is the number of edges times, because we just have to add up the probabilities to the R minus 1. So if H is at most 2 to the r minus 1, then this is at most 1. So we can conclude that there exists a coloring when this is less than 1. Okay? The other possibility that it is always 1. Otherwise, the expected value, if it's at most 1, well, in some colorings, it could be larger or smaller. Obviously, it could be larger than, I mean, if the hypergraph is 2 to the r minus 1, then it contains many monochromatic edges. The average is at most 1, so there should be some coloring where the number of monochromatic edges is less than 1, and that means 0. Okay. So that was the end of the proof. Now, there is a long history of this problem since then. It was, so that's the end of proof. Joseph Beck proved that this M of R is some at least log R times 2 to the R. Later he improved it to R to the 1/3. And the current best bound is still from 2000 by Radishiknan. Rishnan and Srivivara, who improved the lower bound to root R. Well, almost root R. Now, actually there are many extensions of this problem for K colorings. Then the minimum size, well, depends on the range of K and R. If K goes to infinity or R goes to infinity, but basically something like we have a lower bound, meaning we have an algorithm to color if the size of the hypergraph is something like K to the R. You see, K was 2 here. And then R power. The best bounds now I do to Sasha Kostochka, my colleague or former colleague in Urbana, Illinois, Urbana-Champaign. And also by Shabanov, who might know here, not here, but a certain from 2012, who actually proved a very general bound for K colorings, which is always true. That's root R K to the R minus 1. That's true for every R and every K. You know, it's a nice formula. That's always true. Now, there's a square root here. Now, every proof, these lower bounds are something like this probabilistic coloring. Actually, not only that, but as you see here, when we made this random coloring at the first time, we got h over 2 to the r, or 2h over 2 to the r, monochromatic edges. Now, if the size of the hypergraph is only slightly bigger, 2 to the r times root r, 2 times root r, then we got root r monochromatic edges. The idea, what actually was invented by Joseph Beck, that because after the first round we had so few monochromatic edges, we just tried to fix it locally, so make a second round or a recoloring. Okay, so the idea is coloring in 2 rounds, random coloring in 2 rounds. Now, and those proofs are usually rather technical, or one has to be very clever. But here is a beautiful proof of Pluhar from 2009. Well, if you happen to know that proof, I won't tell. I mean, anybody heard the name of Pluhar? Non-Hungarians. Okay, so he's a professor in Szeged, and he made the following beautiful proof, which is actually also work for K colorings, but I now return to 2 colorings. From now on, we will talk about only 2 colorings mainly. So he had this lower bound, 0.52, fourth root r, 2 to the r. And it's surprisingly nice proof. It is also probabilistic, but the probabilistic space is different. This is usually the most difficult part to make a proof using probabilistic theory, that what kind of space we use. So here, coloring the vertices 1 by 1, that's quite natural. So here what he does, he takes the underlying set. Okay, so maybe the underlying set has size t, and consider an ordering, a linear ordering of the elements, x1, x2, xt. We can say a random linear order, or we can say consider simply a linear order sigma. Sigma, how to write sigma? I think sigma. Maybe I use pi. I forgot how to write sigma. So take a permutation from ST. Okay? The permutation group of T elements. Take a permutation, and for every permutation, I define a coloring in 2 steps. First, every vertex is just blue. Okay, that was pretty simple. Now, we didn't choose anything about the permutation yet, and we didn't consider anything from the hypergraph. Okay, so again, what are we doing? Given a hypergraph, which is smaller than this, r to the 1/4, 2 to the r. So given a hypergraph, R uniform, and we want a cut. We want to cut them simultaneously. Now, take any permutation and color all the vertices blue. But that was just the first step. After that, we just visit, we have the edges E1, E2, EM. We have M edges. Now, we just check every edge, EI, where are the elements of the edge EI. And if the element X is the first, then we recolor it red. Okay, so every first element change to red. That's it. Now we got something blue, red. Well, actually the first vertex is probably red because there is an edge there. Okay, so every first element is red. Now, well, we got a coloring. And what is the first observation? What we can see immediately that that no edge is homogeneously blue. Of course, because the first element is always red. So that's okay. We don't have to worry about monochromatic blue edges anymore. Now, what about well, of course, it might possible that a certain edge EI become completely red. Okay, so maybe this EI is all the vertices are red. Now, if EI is red, then it means that every element of it in that permutation, for that given permutation, every element of that edge, that hyper edge, that R subset, turned to be red. So especially the last element turned to be red. So there should be, so if all element is red, then there exists an EJ such a way that this is its first element. So the last element of EI became the first element of EJ. Now, this is very unlikely in some sense. So we can conclude this proof in 2 different ways, either just counting the permutations, or we can consider the expected number of such creatures. But now I do the counting instead. because we will have more probability theory later. So the number of permutations where EI completely before EJ and EI intersect EJ in one element, just in a singleton, okay? Because, well, that was the last element of EI, and it was the first element of EJ, so they have just one common element. So the number of permutations of this type of permutations, we know it exactly. What is this number? Well, EI and EJ has altogether 2r minus 1 elements. So we choose 2r minus 1 elements, their places on pi, and their places on the permutation. We put the common element, well, so you already selected these spots, okay, just the place for EI and EJ. The common element should go to the middle, and we can permute the first r minus 1 element any way we like. We can permute the last r minus 1 any way we like. And then, because we only consider permutations where EI precedes EJ, the rest of the elements permuted arbitrarily. So this is the exact number of permutations such that EI precedes AJ and the intersection is 1. Now, what about the total number of such permutations? So the total number of permutations such that some EI precedes EJ. Well, this is at most, well, we have to choose AI and EJ. There are no more than m times m minus 1 ways to choose it, at most, because maybe the intersection will be empty or maybe larger. And one go first and the second times that number over there, which is t factorial 2r minus 1 factorial r minus 1 t minus 2r plus 1 factorial. It was the binomial coefficient, so we are now here multiplied by r minus 1 factorial, and we cross out. Now, so if this total number of permutations is less than t factorial, then we are done. Then we have a two-coloring. Then we have an eligible two-coloring. Using this greedy algorithm. Well, that's called greedy algorithm, how we did. Okay? So another way, let's do the calculation. What did we got? If m times m minus 1 times t factorial r minus 1 factorial r minus 1 factorial, 2r minus 2 factorial, 2r minus 1. If this is less than t factorial, then we are done. So I think we can see that we can simplify with t factorial, and what is here is just a binomial coefficient, so we got m times m minus 1 is at most 2r minus 2, choose r minus 1, times a 2r minus 1. And this binomial coefficient, as we all know, is asymptotically 4 to the r minus 1 divided by square root pi r. Okay. So what is in the right hand side is something like 2 over root pi, just a constant, 1 over r, 1 over root r. Four to the r minus 1. Okay, and then we are done. This, oh, the 2r minus 1 I forgot. Yeah. So we just take the square root of this one, and this is 2 to the r times 4th root r. So that was the algorithm. Now, I forgot to mention that actually we are more interested in the upper bound. So that was Pruhar's proof. It is a beautiful proof, and somehow it shows that somehow the almost disjoint pairs which are causing troubles. But and it's conjectured by Erdos that m of r is probably r times 2 to the r. But this is just a conjecture. What Erdos proved instead, and that was one of the first truly probabilistic proof, in the early 1960s, that he proved that m of r is at most a constant times r squared 2 to the r. Now, I told here that we need a construction. We need a construction of 3 chromatic hypergraph, something like this 2r minus 1 choose r. Now, instead, Erdos made a probabilistic construction, a non-constructive construction, and that construction is what we will use later and generalize. So what he did, he reformulated the problem in the following way. What we want, what we really want here, m of r, is that we take an underlying set S, and we just build our hypergraph. We build our 3 chromatic. We want a 3 chromatic hypergraph on S. What we do is this. For every cut, if we have a cut S1, S2, we just, for every cut, we select an R subset here. Okay, this is what we need. For every cut, we want to put an R subset there. Just like here in 2R minus 1 choose R. Actually, in this way, here we took all the R subsets. So in every cut, in the larger part, we put a R subset. Now, this is what we are going to do. And we take, so that's what Erdos did, that he just, just a minute, I'm sorry. Yeah. It is clear that whenever we take an R subset from the here, then it so what we need and EI is subset S2 in every S1 union S2 cut. Now, what he observed that if we have a n element set, then we just select an R subset from every, okay, so we take an R set, E, I, from every set X, if X is at least S half. Okay, so actually instead of N I use T. So we just want to select a subset from every T element set. Now what he did it in a probabilistic way, and the main observation is that if we select one set E, then this E belongs, or to many X, many sets which size T half belongs to many T half element sets. Okay, so a single R subset, so this E belongs to, we know exactly how many. The E is belongs, I covered, included. So the number of X where E is covered by X, we know it exactly. It is, well, R elements are given, so we have to choose out of, not N, but T. From the rest, well, this cut is somewhat skewed, so we take N half elements at T half. We already have R elements, so we want to choose another T half minus R. Okay, so T half subsets. Now, and what he observed that this is awfully lot. It's a large fraction of the T subset. So if we divide this by T choose T half, then this is nothing else than T times T minus 1, T minus R plus 1, and the denominator here is T half minus 1, T half minus R plus 1. So if T is large enough, then this is about 1 over 2 to the R of the sets. So he proved the following statement, that and that was the core step. Of course, we have to choose T properly. You see, this is always about 1/2, but it's not really 1/2. It's somewhat less. So this is 1 over 2 to the R times product of 1 minus R over T minus R, roughly. And this product is something like asymptotically. We have R members here, so this is 1 over 2 to the R. We still have 1 over 2 to the R, and this product is 1 minus R over T to the R, which is e to the R square over T, negative R square. So if T is too small, then this will be a big exponential, I mean a very small exponential term. So we have to choose T. T will be around R square. So that's what he did. And in this case, just selecting one member, we cover immediately 1 over 2 to the R times a constant number of T half subsets. Now, to cover them all, we have to take more than, well, of course, many R subsets, and actually the calculation shows that if we take R squared times 2 to the R, then that will do it with high probability. Okay? Now, now we start a slightly different topic, which is why Erdos and others were interested in these hypergraph problems. And one thing they were interested in, because they were interested on least chromatic numbers. Okay, so of a graph G. Now, the least chromatic number is okay. So first, given a graph G, and given an assignment for every vertex, a set, a subset. From some underlying set, but that underlying set is not interesting. And we say that this assignment is well, I want to use the proper words. It's choosable. So we say that G is a definition. G is L choosable. If there exists, we can select from the list. There exists a function from every L. We can select a member. We can select a member C of V. Such that C of V is from L, and for every UV edge, CU is different from CV. So, in other way, it's a good coloring. C is a good coloring. Now, and the least chromatic number of G is, well, maybe a little example first. The least chromatic number of the complete bipartite graph 3, 3 exceeds 2, because we have this complete bipartite graph here, and we assign lists 1, 2, 1, 3, 2, 3, and the same on the other side. Now, this assignment is not choosable. Because everything is symmetric, so from 1, 2, we have to choose either 1 or 2, and if we choose, say, 2, then on the other side, we have to choose for this vertex. If we want a good coloring, then we have to choose 1. In this vertex, we have to choose 3. And then in this vertex, we are in a big trouble, because we cannot choose either one. No, not this vertex, this vertex. We are in trouble because there is no choice. We cannot choose either 1 nor 3. Okay? So there is no choice. So, now, it is also easy to prove that for every graph, if every list is at least the maximum degree plus 1, then this assignment, this L of V, is choosable. Indeed, we can do with a greedy algorithm. we can never get stuck like here, because if the lists are long, whenever we are here, we look around, there are 3 neighbors, but we have a list of size at least 4, then we can always have a free color to choose which were not occupied by the neighbors. Now, there is a deep connection between least chromatic number, and the least chromatic number is the smallest. Okay, so least chromatic number, did I write it down? Yes, not. Is the minimum S, such that if every list size is at least S, then L is G choosable. Now, so we already have the least chromatic number is at most the maximum degree plus 1, and also it is obvious that it is at least the chromatic number, because if we have the same, well, so maybe I write in this way, is bigger than the chromatic number minus 1. Because for every L, we just have the same list. And this is not choosable. Not G choosable. Because otherwise we can color with smaller number of colors, by definition. Now, what there is a deep connection between property B and least chromatic number of the complete bipartite graph, because as you have seen here, we have 1, 2, 1, 3, 2, 3. It's just like the same hypergraph, like this one. If we have a complete bipartite graph of size M of R, then that's a complete bipartite, a huge complete bipartite graph. You know that M of R is at something like 2 to the R. Then, and we put the lists are the subsets. Okay. Just like before. Then exactly as in this proof, this assignment is not KMM choosable. Well, because if we select, well, we have a set of colors, and we have some colors on the left side that we call S1. We have some other colors on the other side, S2. And what went wrong here? Then we will have an R subset E completely on the let's see. Why is it wrong for us? It's oh. Then everything on the other side, oh, well, because it's completely on one side, but this list appears on the other side too. So every vertex has a pair, has a mate with the same list. So if we select a color here in EI here, then we cannot select that color on the other side. So actually, every coloring provides two coloring of the hypergraph. So it's exactly the same problem. Exactly the same problem. So we got that the list coloring number of MR exceeds R. But the list coloring number of so in this way we got that the list coloring number of K MM is something like log 2M. Now, this notion, list coloring number, was introduced by Erdos, Rubin, and Taylor. More exactly, that's when it was, I think, when it became a famous problem. But actually, it was introduced earlier by Zhikov in 1949. But he just introduced it and proved these basic inequalities. But so actually, list coloring is a very natural notion. It comes up in every kind of coloring problem, because what happens, we have a partial coloring of a graph and we want to continue. So this means that for every vertex we already have some colors which are occupied, which are forbidden. And so the available colors, the list of available colors are shrunk. And so it's a very natural problem. Now, the result I wanted to show you, and I show in the last 10 minutes or so, is a joint work it's a joint work with my former colleague and students, Alexander Kostochka, again, and Mohit Kumbhat. Now, basically, what Erdos did, he generalized this result for K colorings, and he showed, where is it? I'm sorry for yeah. One page is missing. Yeah. Yes. So actually, what Erdos proved for K colorings is proved that if R is sufficiently large, then there exists a hypergraph H such a way on T vertices, well, actually K times such that this hypergraph is small, well, there is a constant R square K to the R minus 1 K to the R times log K. Okay, so this is what Erdos did. Well, actually, he did not do it, but the same method gives, so it's not interesting. Now, so what we are interested in is not, we are interested in the least coloring number, not the complete bipartite graph, but the complete k-partite graphs. Okay, where k is fixed and m goes to infinity. Now, it is known, and it follows from Erdos' work, that actually this coloring number is something like maybe I shouldn't put down. It is it is 1 plus little 1 times log k over log k minus 1. What? No, log, no. Log k over k minus 1. M. So in another way, here, if the list sizes were R, then these groups grow like 2 to the R, roughly. But in the k-partite version, it grows like it grows like something like k over k minus 1 to the R. So this was an old result. And what we did with Sasha, Kostochka, and Mohit is not this one. We strengthened this result in the following way, that now we introduce one separated least chromatic number. Now, this here is yeah. So for any graph, instead of the usual least chromatic number, we can introduce the C separated least chromatic number, which is the minimum size of lists minimum size of, we use the same notation over there. There was some now. The minimum number S, such that if the lists, every list is at least S, and these lists are almost disjoint, so at most C. So we require that for every edge, we require that the lists should be almost disjoint. So we cannot assign the same list over and over again. That would be too easy. You see, it's for the bipartite graph, if we have the same list 1, 2, 1, 2, 1, 2, then we can color with 2 colors. But if we have arbitrary lists, even for the complete bipartite graph, we need list sizes of log n to get a good coloring, to get a good choice of colors. Now here we further restrict the eligible lists such that if we have an edge, then the lists are almost disjoint. Now if there is no restriction on C, we got back the same, or the restriction is like S, then we got back the original list chromatic number. So G1 is usually larger because there are more restrictions. Okay? So the minimum is larger. So we have this easy constraint, and actually this notion was introduced by Kratok here, an excellent Czech mathematician who proved with Tuza and Voigt for different class of graphs. And for example, they proved that the list chromatic, the separated list chromatic number of the complete graph, now I take Kn, is for, so the advantage of this result is again true for every n and every s, is something like 2e is a number, not the number of edges, s times n, and a similar lower bound, 1/2 s times n. So especially if s is 1, then the least chromatic number is root n. So now I see that here I made a huge error. It goes the other way around. Because the least chromatic number of the complete graph is obviously n. Okay. So what we are going to prove in, there is a watch, is our result with Sasha is something, a strengthening of the old result of Erdos for one separated least chromatic number. So we prove that the same result k times one separated, it is again 1 plus little o 1 times log k over k minus 1 m. As k is fixed and m goes to infinity. Now, to do this, we need, just like here, lists, but now, so we need lists in such a way. Here we needed something which was 2 chromatic or 3 chromatic. Now we need some hypergraphs. We need some hypergraphs which are k chromatic. And not only that, also these hypergraphs are relatively big. And we also want, well, there are other terms here. And we also want that, because these will be something. So we want that those lists, those hypergraphs, are kind of orthogonal to each other. So if we take an edge, take a list from here, EI in HI and EJ in HJ, then AI and AJ should be almost disjoint. Now, to do this, we improve Erdos construction in the following way, that Erdos just took R square elements. Now we have yeah. So here's our main lemma to finish. That if we have let me copy instead, because I will leave out some condition. So if we have 1, 2 Q classes, each of them is big, and we choose Q very carefully. It will be something like R square over a very small constant. And then we can select R subsets, not too many, such a way. So that's the main point. Our aim is, just like in Erdos problem, Erdos proof, that we need a hypergraph, H, such that every R subset is a transversal. So for these sets T1, T2, TQ, every element is transversal, and what we need, that the largest empty set. The largest, so every set X of size larger than this same A times TQ, this is the size of S. So every positive fraction contains a hyperedge. Okay, so that's what we want. That's why when we choose A appropriately, A small, immediately we see that the chromatic number of such a hypergraph is at least 1 over A. Because, well, whenever we have a partition into A less than 1 over A groups, there will be a large group, and that will contain an edge. So this is what we want. And this can be done cleverly in such a way that the size of H is at most 1 over A to the R times 4 TQ. So this is the main lemma, where the proof is probabilistic, very, well, somewhat similar what Erdos did. And then having this lemma, because here to prove this statement, we need a construction. We need a kind of construction like here for the risk chromatic number of bipartite graph. We need a construction now where we have k parts, and to do this, we just construct one hypergraph where alpha H1 is less than the size A times 1 over K times S. And then, because we can choose any fixed number, and then if we have one such hypergraph of size something like K to the some R subsets, so you have K to the R to the K. Then we make several copies of this. Several copies, something like R square over A copies. And then we put another hypergraph across. This will be H2. And then we take these blocks from H2, larger blocks, and we put R subsets across. This will be H3, and so on, up to HK. So that's the proof in one sentence. Of course, some technical details left out, but the statement is actually that the risk chromatic number of the complete k-partite graph is about the same as the one separated risk chromatic number, as k is fixed and m goes to infinity. Maybe I can mention that actually there were earlier results by Krivelevich, who proved somewhat weaker versions. I mean, he proved a smaller order of magnitude, but we finally finished and made a asymptotic. So, of course, several problems remain open. And thanks for your attention.